Alright, the last part of the 4.4 notes is looking at, since most of the stuff we're doing in 4.4, and it'll be true, most of the questions that we'll ask you will be exponential base equations. So exponential growth, either uninhibited growth and decay, or logistics, which has exponential functions. But I wanted to do a couple of simple examples that involve logs, because logs are, again, functions that show up. The natural log occurs in nature, and they do show up in some applications. Alright, so the first application here is one that I found that the strain, which is in terms of the percentage of compression on the lumbar vertebral, in an adult person is based on the load, right, in kilograms. So X represents the kilograms of the load, and that's how much your vertebrae will, the percentage of compression on your vertebrae. Alright, this is given by this fun function, right? This fun logarithmic function. And again, real life examples tend to be a bit ugly, and this one is ugly. Alright, we want to know when the rate of change, what's the rate of change of the strain with respect to the load when the load is 500 kilograms. Now, you could solve it graphically like we did with the logistics equation. You could graph this equation and find its derivative. Graphically, you just have to make sure your window's big enough, make sure your x maximum includes the 500. Alright, so you'd have to go big enough to make sure the 500's in your window, and you could find your derivative. And you can check it, check my answer that way on the graph. I am going to solve this beast by hand because I think it's just good practice to show you the derivative of this by hand. Right, the biggest thing with this is just mind all of the numbers, the ugly numbers. Alright, so it is just a simple log function of a function. So it is the chain rule. No other rules are involved, it's just the chain rule of the log, because it's 7.3, which is a constant multiplier, it's going to come along, times the log of that expression inside. And so when we take the derivative, right, we want the derivative because we're looking for the rate of change. 7.3 is a constant multiplier, it's just going to come along. It's the derivative of the natural log, which is 1 over the function that's inside, exactly the same, right? You don't change anything about this inside function. And so it's 1 divided by that 0.0645, x raised to the 0.91 plus 1, alright? So that's the logarithmic part, 1 over what's inside, but we're not done yet. Chain rule is then I have to multiply times the derivative of the inside. So again, I just look at the inside function, and it's a power function. It is a power rule. It's an ugly power, but it is just a power rule. That 0.0645 is just a constant that's come along. My power rules, I pull out that power, 0.91, and multiply by it. So it's the decimal out front times the 0.91. X raised to the degree where I subtract 1. So I'm going to take the 0.91 minus 1, and that's going to come out negative 0.09 when I do. Alright, then 1 is a constant, so it zeroes away, and so that's it. There's my derivative of my numerator. Now I'm going to rewrite it as a single fraction. Again, this is a minor step. You don't have to. And I'm not going to multiply any of those out because I'm just going to plug them into the calculator as is. So it's up to you if you want to multiply them out. But I'm going to leave them exact so there's no rounding. So I'm just going to write my 7.3 times that 0.0645 times that 0.91 times x to the negative 0.09. Up top and in the bottom, it's that 0.0645 x raised to the positive 0.91 plus 1. Alright, there's the function that I'm going to use to find my rate of change. Alright, so it's an ugly function. It is, and you might want to solve this by graphing it, and you can check my answer graphically, and I would encourage you to do that, right? Graph it out and find the derivative similar to what we did with the logistics cases. Alright, but I'm going to plug my 500 in. The biggest thing is just make sure you're careful, right? Up top is just a big multiplication step. It's going to be the 7.3 times those two decimals times, and this is where I plugged my 500 in. My 500 raised to the negative 0.09 up top. Alright, that's my numerator. And then in my denominator, again, good idea to put parentheses because of the plus 1. Divided by that decimal, and again, this is where 500 is going to go, raised to the 0.91. Alright, if you do that, I'm going to round a few decimal places, so when you type it in, it should come out 0.0126. Remember, that's not how we leave the answer. Alright, we answer the question with appropriate units. And so what's the rate of change? Alright, the rate of change is the percentage of compression is increasing by about 0.0126% per kilogram, right? Because the load is in kilograms, so it's per kilogram, right? And so that's the unit. So the compression is changing by that percent per kilogram when our load is at 500, all right? So that's how much the compression is changing, the rate of change. So it's increasing by a small percentage at that time. All right, so that's an example of a logarithm. All right, the last one, which again is another example of a logarithm, a simple example. We're given the price-demand function for a particular type of yacht, Viking boats, yachts, given by that price-demand equation. So P is the price per yacht in hundreds of dollars. So I've got to keep in mind that my answer is in hundreds of dollars. X is the number of yachts demanded. All right, so my price demand is, and so I'm going to write it down here. My price demand is 200 minus my 0.01x times the natural log of x. What is the rate? What is the rate of change in price with respect to the demand for the yacht when the market's demand is 5 yachts? So I need my derivative, right? Rate of change. And I'm going to plug 5 into it. All right, so the derivative of the price demand equation. Well, that's just a constant. So that'll zero away, but here is not. Now I'm going to be careful. I'm actually going to put parentheses around this. That negative is going to come along, and I'm going to put parentheses around the derivative. The negative is a constant multiplier, and so it's going to come along. And then I'm going to take the derivative of the natural log part. All right, there are two functions. There's this 0.01x, and there's the natural log of x. I am going to have to use my product rule. And so the first function, 0.01x, times the derivative of the natural log, which is 1 over x, plus the natural log, times the derivative of the 0.0x, which is 0.01. Alright, and then simplify that. Alright, don't forget there's the negative out front. So this x value we reduce with this x value, so I'm left with the 0.01 plus 0.01 times the natural log of x. Now you could factor out the 0.01, and it's up to you if you want to do that. The biggest thing is don't lose the negative. It's really easy to lose that negative. Alright, now I'm ready to plug my value 5 in, so I'm going to find my derivative of the price equation at 5. So again, I'm going to plug 5 into this equation. So 5 goes into the natural log part, and then I'm going to round a few decimal places. Comes out negative 0.026. Right, remember, that's not my answer. I've got to answer the question with the appropriate units because it's an application problem. So the demand, the price demand, and the price demanded is decreasing, right, because it's negative. That's why that negative is important, because decreasing is very different than increasing, at a rate of, well, remember, the function value, the price, was in hundreds of dollars. So decreasing at a rate, and for some reason I can't go, there we go. Decreasing at a rate of $100, right? And so I've got to keep that in mind. So decreasing at a rate of 0.026 per yacht. All right, because the x value is in yachts. All right, that's one way you could do it, or you could multiply this out by 100 and change it to dollars per yacht if you wanted to. So an alternative to this could be at a rate of, so it's still decreasing, at a rate of 2.6, so $2.60 per yacht. That's an alternative. So either of those would work. This would be, if I multiply this by 100, right, so this $0.02 is the same as $2.60. And it's still per yacht. X is still in terms of yachts. And so either one of those would work. So price demand is decreasing at a rate of $2.60 per yacht. So it's not decreasing by much. All right, that finished up 4.4. So we're done with 4.4, which means there is going to be a Kinect quiz. All right, so make sure you go and get on Kinect and practice some of the Kinect problems to prepare you for the quiz. The quiz will be open on Friday. And then again, make sure you get on and do that. Alright, and then there will be a test coming, and I'll talk about that in ReggieNet. Alright, so I'm going to wrap up the video there, and that finishes up 4.4.